Okay, my outstanding friends, this is going to be fun. Did you realize that NASA has figured out a way to milk an asteroid? I'm not kidding you. They figured out a way to milk an asteroid. Wait till I tell you. Okay, so what are we talking about here, milking an asteroid? How could they possibly do that? Well, this is Asteroid Bennu. They took a spacecraft, went up here and went down here, and pop, they grabbed a sample of this and brought it back to Earth. All right, so that's the beginning of the milking phase. They landed a spacecraft on here, it was a touch and go. It went bam, and they took right back off again and grabbed a handful of debris from this area and brought it back to Earth. So how does that play into milking an asteroid? Well, let's think about it. Okay, my wonderful friends, this is from space.com, and they say this is all you need to know about asteroid sampling the mission OSIRIS-REx, which went up to this asteroid called Bennu. It went down, grabbed a bunch of it, and came back to Earth, and now it's headed back out to do another sample of another asteroid. Now, here's exactly what happened. They call it the OSIRIS-REx. It's an ongoing mission. It returns samples of asteroid Bennu, which I'll show you in a minute, to Earth on September 24th, just a few months ago. And I posted back then, I knew what this sample was going to be, and I will show it to you very shortly. And it is now moving to study asteroid Apophis in 2029, which is going to come close to Earth as well. Now, this is what they're showing. I think this is an artist's representation, basically, because I don't know how they would take this picture. But what they did was they came down into this little crater and grabbed a sample and popped right back up and headed back to Earth with this bunch of stuff. Now, here's exactly what it says. All right, OSIRIS-REx from NASA is an ongoing mission. It visited and collected a sample from asteroid Bennu and returned the sample to Earth just September 24th, 2023. That's only about 4 months ago. The spacecraft is headed to a new target, this asteroid Apophis, which will also fly close to Earth in 2029. They're trying to see what these things are made of. They have no clue. It says that the OSIRIS-REx launched in 2016. That's 8 years ago. It arrived at Bennu in 2018. It began orbiting the carbon-rich, remember that, rock on December 31st, 2018. A dramatic yet brief touchdown. It just went bang, just like that. On October 20th, 2020, saw Bennu pick up a sample from the surface before beginning the long journey back to Earth on May 2021. OSIRIS-REx sample return capsule brought a sample of Bennu back to Earth at 10:52 a.m. Eastern Daylight Time on the 24th from 2023. But that will not be the end of the main spacecraft's mission. It will be retasked to swing by this other asteroid in 2029 with a new moniker, OSIRIS-REx Apex. This is how you milk an asteroid. Okay, here's their explanation. OSIRIS-REx sample mission return. Here goes.
How does one spacecraft image an asteroid from as far away as 1,000,000 kilometers, or as close as just a few meters? Accomplishing this task is the job of OCAMS, the OSIRIS-REx camera suite. NASA's OSIRIS-REx mission is headed to near-Earth asteroid Bennu, a remnant from the dawn of the solar system. OCAMS sits on the OSIRIS-REx instrument deck, which will face Bennu during orbit. It consists of 3 cameras built by the University of Arizona, each designed to provide the mission with a unique perspective. Polycam is a reflecting telescope with an 8-inch mirror and a narrow field of view, which will acquire both long-range and close-up images of Bennu. MapCam is a medium-angle camera, which will map Bennu in color. SamCam is a wide-angle camera that will record the most crucial moment of the OSIRIS-REx mission. OSIRIS-REx will spend nearly 2 years traveling from Earth before approaching Bennu in 2018. Polycam will be the first instrument to spot the asteroid as a faint speck of light up to 2 million kilometers away. As OSIRIS-REx approaches Bennu, it will switch from navigating by using radar ranging from the Earth to using OCAMs to refine the asteroid's position and to ensure a smooth transition to proximity operations. Over the next year, the OCAM suite will scan Bennu at various resolutions, providing global maps and close-up images. MapCam will use its color filters for spectral imaging, revealing clues about the asteroid's composition through subtle changes in its color and brightness. In 2019, OSIRIS-REx will make a series of close passes of Bennu, allowing Polycam to image portions of the surface with sub-centimeter resolution. These images will prepare OSIRIS-REx for its most important task, which will be documented by the wide-angle SAMCAM. After more than a year in orbit, OSIRIS-REx will slowly approach Bennu's surface to grab a sample of the asteroid. SAMCAM will capture the event in a series of rapid-fire images. This visual record will help scientists understand the context of the returned material. In 2023, OSIRIS-REx will deliver its sample of Bennu to Earth, where scientists will study the sample for decades to come. OSIRIS-REx is investigating Asteroid Bennu, and OCAMs will provide the first close-up look at this ancient remnant of the solar system, revealing clues to Bennu's history and our own.
Okay, that is their take on this, and I say this is how they milk asteroids. Okay, listen to this now. They're going to be going to this other asteroid, Apophis. In 2029, they should reach this asteroid out there. That takes another $200 million after the $800 million, so it's around $1 billion. And I believe that's just in the cost of the mission expenses. Then you have hundreds of scientists spending 20, 30 years examining this stuff. Okay, so here's my claim, and this is what they're going to find. Lithium, beryllium, vanadium, chromium, all of these different metals and so forth in these basic quantities in relation to each other. And they will also find this, again, these quantities in relation to each other. And they will also find these quantities in relation to each other. This is what Bennu sample will be. And how can I make these claims? Because this, my friends, is what's in whole blood, plasma, and serum. So why would I expect that to be on Bennu? Well, because Bennu's a heart. All right, I would say for NASA to hire some biologists and anatomists and see what biology and anatomy is, because that, my friends, is a heart. There is no question whatsoever about that. And here is another heart called Psyche, which is out there, the same thing, only this one got too close to something really hot, and it smelted a little bit of the blood, turned it into metals. And that's what happens when blood reaches 3,000 degrees or more. The metals begin to show up as metals. They flocculate into metals. You know, okay, you should be able to see all these at the same time. It makes it much easier. These are the heart valves. This is Bennu. This is Psyche. This also has all the plumbing of the heart, and they're both made out of metals, which means that their blood is made out of primarily metals. And I gave you that chart, or I will give it to you, that shows exactly what the chemistry of blood is. And there's 3 different styles of blood. There's the plasma, there's the whole blood, and then there's the serum. And there'll be different varieties in there. But each one of these grains that they picked up off of this spot right here. All right, now don't forget, that's a heart too. You see where the tubes are coming out of the heart? And you see that white stuff right there? That's this white stuff right here. I'll show you this very carefully, because this is the tendinous material that wraps around here that attaches to the muscle, so the muscle has some anchor. That's what this is, the anchor. And then, of course, the valves. Now, this is where they landed right here. Anybody that's been with me for any amount of time knows that red and black is blood. That's it. And the yellow is lymph, or it is also a transitioning phase of the red blood towards the black blood. You have vein and you have artery and you have lymph. And I've shown this hundreds and hundreds of times. It's getting very tiring. They landed here, grabbed a sample of this, brought it back to Earth, and I showed you what the chemistry is going to be. Why can't they just use the scraps? They have scraps that they're just, I don't know what they did, threw them away or whatever they did with them. They could test that. It's the same stuff. I don't care about looking for microbes and bacteria. I care about looking for the chemistry. All right, like I said, NASA and all the rest of them got to hire some biologists, some anatomists, and all forth. These are the valves of the heart. You see these valves, these two here? The blood comes this way and it can't go back. A valve means you go one way, you don't go back. These are the opposites. They go this way and they can't come back. Now, this is the architecture of that plumbing of the give and take of the valves. All right, let's start with that. All right, you see this? This is blood going this way, this way. This is blood going that way, and the aorta and so forth, the supravena cava. These are the chambers in the heart. And the heart literally twists. And when it does, it pulls in one side and pumps out the other side. It's a very, very cool system. Now, there are tubes running all over the heart. There's tubes running in and out everywhere because it's a pump. All right, and it has to take good blood in and then send it back out, and it has to take bad blood in and send it back out, and it has to take lymph in and send it back out, and it has to be all separated, and that's a very, very complicated device, but very, very cool. All right, I'm going to make an anatomist out of you in 10 minutes. Very simple. That's a heart. I don't think anybody's going to question that. These are the main tubes. I don't care what you call them. They're the main tubes, and they run down into valves, which I showed you. They can only go one way in and one way out, and that's it. They're one-way valves. Now, this white stuff is an anchor. And when I say anchor, what do I mean by that? These here are all the muscle fibers. These can go like this. This can only go just barely move, but it's anchored tighter than hell down here. But there's a zillion fibers, and every fiber connects to a muscle fiber. It's connective tissue, connective from the heart itself, the core of the heart, out to the muscle, and that muscle actually twists. It's very interesting. I tell you, you can learn a whole lot on the internet. You don't have to go to schools and have somebody tell you this or that, because they don't know. They haven't done the research. I'm telling you, I'm not kidding you. So anyway, what happened here was all of this stuff basically is gone from Bennu, and we're down where the valves are. All right, so let's look at Bennu again. Don't forget, this is the white stuff that I'm going to show you in a second. This is the goopy stuff that goes right next to where the valves are. It's just impossible to not understand this. All right, there's your valves right there. So all that other stuff is basically removed, and you can see the coloration of here. That is the coloration of blood, my friends. This right here, these little, you can actually see the fibers if you can look close enough. Let me see if I can get a close-up shot of that. You see the fibers coming up there? And this is a true high-resolution picture. They were right up there. And that's what is sticking up, and that is the tendons. All right, so don't forget, when I showed you the other heart, it had the big tubes up here. Remove all of that stuff, you're down where the valves are inside, and this is the tendon. The goopy red stuff sort of erodes away. Now, what else can we see here that would indicate it's a heart? Well, of course, the valves. And then we see these tubes. It's a tube. What's a tube sticking out? Oh, there's another one. There's another tube. I think this is another tube too that's down in part of the valve. I don't know, but I think almost all of these are tubes. You got a lot of plumbing going on in the heart. And there's just no question whatsoever what it is. It's impossible. And they have a sample of it. All they have to do is take the scraps and look at it now. 10 minutes they're going to know what's going on, but they want to go 20 years or 30 years or more to study this with all kinds of hundreds of people, thousands of people, and all these research labs and so forth. This is how you milk an asteroid. It's exactly how you milk one. Okay, you see this? This is Psyche, which is another heart. It's another heart. That's what it is. And these are the same valves here. And it's got the same plumbing and all this stuff. Look at this one. I wish I had a better lighting of that, but it looks like it's got the filaments of the valve, which has fibers in it. It's floppy and it moves around, but it's got fibers in there, like an umbrella almost. Think of it that way. Now, you see all of this stuff here burnt up looking, well, not burnt up looking, but smelted, melted. It's blood that has turned into iron. Now, I have some iron meteorites here, which are also biological, because that's biological. Now, this right here is this is what they call a stony iron meteorite. All right? Only the blood turns to iron. This is actually bone. All right? There's no magnetism there. But where you have the blood that cooked up to 3,000 degrees, all of the cheap stuff goes and you end up with the metals. That's why I'm telling you, the metals that they're going to get out of Bennu is going to be exactly what I said. It's blood. Now, this is a little iron meteorite too. It's a tiny one. And I know exactly what it is. And it's a lung. All right, the lungs are saturated with iron, and I can show you that because it has the latch on here I call the spurlock, which attaches this lung into the body. It has all the fibers and the fascia, and not only that, it has all the little holes and alveoli, and I've done catalase tests on this, and there is enzymes in here that react with the hydrogen peroxide given off the gases. That tells me that there was, well, it's just still active enzymes. I don't know about DNA, but it's in here. Whatever it is, this is an iron meteorite. And that's the only way you can get iron from blood or anywhere is to smelt it. And to smelt it, it takes 3,000 degrees. So it doesn't happen, like this would have burnt first. But coming through space, it's a whole different situation. You're in the ionosphere. It's totally different because all you're doing is being saturated with electrons. Now, if this comes in the correct way with the right way of the spin of the Earth, it doesn't explode. Some of them come straight in, boom, they explode because they get so hot so quick. But if it comes in sort of slowly with the rotation and it's in the right orientation, it'll cook until it burns up and it won't fall apart. There's a gigantic heart. Not heart, a lung. A gigantic lung, just like this. It's 100% iron. Well, not 100% iron, it's 100% metal. And it's the Willamette meteorite. And it is a lung. And it's still got some alveoli and a little bit of blood in there. Now, everything I have found in space, 100%, not a single thing, has been just nothing. It's all been body parts. This right here is Comet 67P. This goes back to 2015. Now, the reason I say they can milk all these things is because I reported this to NASA and all of them, everybody, to Yale, to all of them. I said, this is biology, my friends. That is an artery blowing out here. That's not just dust. That is cooking. And the astronauts say the space smells like steak. They go out on spacewalks, they come in, they take their suit off, and they smell sirloin. Now, this goes back 8 years ago, 9 years ago. These are the blood vessels, the tiny stuff, and it shoots out in the direction that the thing is pointing. And this, my friend, is a hip socket. And can I support that statement? I believe I can. All right, this is from a different angle. That's the hip socket, and this is the neck, and then it comes out like this to join into the body. So let's see what that looks like. Here it is right here. You see this? This is it right here. All right, the neck, and it breaks right here. They can break in a bunch of different places. Sometimes they break right at here, and sometimes they break up here. But it's all from the hip joint. And it could break up higher up here or wherever. Doesn't matter. But it's this particular is exactly what we're looking at. All right, so here it is right here. There's that ball that's in this socket. Here's the neck, and it broke off somewhere up in here. There's all of these connective tissue, which is nothing more than little tendons running up the side of that thing to connect the ball so that it can twist a little bit, and it's not rigid, solid. You need tendons to be able to move things just a little bit. This is a very complicated device. All right, and you do see those tendons right here. Whoops. These are those tendons. And that's a bundle of tendon that runs up to some, it has to run a couple different directions because it has to be able to twist this way and then pull itself back. So you've got opposing things going on here. And they landed right down in here and took a sample of that. And I had the spectral analysis of it. And it's all biology, same stuff. It's all, primarily they looked for the iron, which is, all the levels of iron were in there. They're different, because you have, iron is your blood. Blood is basically iron. And all those transition metals, the same metals I showed you in that chart. And they are, well, here it is right here. These are the transition metals. And what they do is they have oxygenation states. They can attach and detach very easily to create what's called nucleophilic substitution and invasion. So in your body, your blood moves around with this stuff. And they grab with what they call a ligand. They grab on a pincher and they say, okay, you want this thing? Give me 2 of those electrons and I'll give you this. Boom, boom, done. Out it goes back to get recharged through the liver, through the heart, through the lungs, all that stuff. Picks up all kinds of enzymes as it goes through your body. This is extremely interesting stuff. But this is what they're going to find from that sample of Bennu. It's as simple as that. And they're spending, this is over $1 billion just for this part of it. And they, this goes back to 2015. Or even more earlier now, I think I reported this to NASA. I said, take a look at this. And they just, I can't remember what the resolution was, but basically you're insane. Now, this artery, remember here? This thing's not a puppy. This is like I say, this is February 2015. I was starting to really accumulate all my notes and my data about this. But before that, I think it was 2014 that they really started presenting all this information. And they were forthright with it. I had no problem. Even the spectral analysis and all of that stuff, I got it all. Anyway, this is very big. That one artery right there is 500 feet across almost. 40 meters is here. Boom, boom, boom. It's like 4 of these. It's 160 meters times 3-ish. You're around 500 feet. And these are, all these little ball spots are where the blood infuses in. You have to have blood on every single cell in your body continuously, over and over and over and over, fast. Now look at this. They landed down in here. All right, this is the pyramid, the Great Pyramid, somewhere down around where they landed. That's how big this thing is. You want to see Raleigh, North Carolina? Check this out. Boom. Here's Raleigh, North Carolina. That's how big this thing is. It is not small. Now, these creatures were, as they said in the ancient texts, they were gods. All I can tell you is this is what it is. Is what it is. Even Omaru Maru. Look at this now. Take your time, and I say, get an anatomist. Get somebody that knows biology. This little peeled back stuff here is what's called grip skin. It's like the skin that's on your fingers, and it is a thick rubbery pad that's on your fingers, and it peels right off. And I have the exact same conditions here. Now, this little ball right here is what's called an apical tuft. These little straps you see coming down here, they come up, they lock in here, and these are all tendons. Now look at this white stripe here. See this white part right here in the middle? And then you see all these little boom, 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 and a split here. And then the exact same thing on this side, and then going down this way. That's the joint of your finger. All right, this is the apical tuft right up here at the top. that locks so you can make these movements. And that is the rubbery skin that's on your fingers and your palms of your hand and your feet. It's very thick, and it's a lot of collagens and keragens, a lot of silicon. Totally different than underneath. The basement layer, absolutely totally different. There's virtually no blood in here. All the blood is down below, and there is a ton of it. Now, if we follow this all the way down for the joint of the finger, and then coming down this way, that is where the vein blood was. You see it black? This side here, you got the same exact architecture, but you don't see it because that's where the artery was. And then down here, these are both tendons. That's your finger laying this way so that you can go this way and that way and all that. There's all these little tendinous material. You see them coming down here? That lets you do all these kind of things with your finger. All those straps coming up, and that's hinge basically. All right, that's a Maro. Avi Loeb from Harvard is absent without leave. No, I've tried over and over to contact him because he's saying this could be a spaceship. I figure, well, maybe the guy's at least willing to think out of the box. Not for Roger. All right, so I was not exact on what I told you before. It appears that it's 2,500 degrees or so Fahrenheit, where you can smelt hematite, which is red blood basically, into iron. All right. Now, this is the red blood that was probably in marrow, that was inside a bone. All right. This is a bone, and I probably should show you this in a microscope. But this is the blood, and you can see the blood actually boiled. Now, why didn't it explode? Why didn't the bone burn right up? Why is that? With a torch, it would have burnt up. To get this to 2,500 degrees, you would lose that bone. There would be no bone. It would be blackened and charred and destroyed. How could it possibly have maintained its boniness and still end up with iron in the same piece? It seems impossible, but I understand why. Because it came through the ionosphere. And the ionosphere is in this temperature range, but there is no impact. It's not like there's no burning. It's just infusing with electrons. So it leaves the bone intact. Now, some meteorites will explode. Depends how they enter the atmosphere, whether they're coming in with it, against it, down. It depends, because the Earth is spinning and the meteorites are coming in one angle or the other or straight down. So all of that plays into account. But this is the only possibility, is this is the ionosphere's temperature caused this to turn into iron and smelt off all the other stuff in the red liquid blood. This entered our atmosphere as liquid inside of a bone. It's the only possibility. And it expanded and broke the bone apart, yes. Because otherwise it would have been a bone just like this. Let's say it was this kind of a bone. Inside there, it's saturated with blood, literally saturated. It would expand, yes, because it's heating up inside. The bone doesn't have the same absorption. And then it would explode this away, and you would end up with this. All right? I hope that makes it crystal clear. Let's see what the temperature of the ionosphere is, which is where this thing is going to be coming through to have this happen. All right, this is important to understand. The space station and all that stuff is up over the top of our atmosphere, outside of our atmosphere. Well, our atmosphere ends up being out here. In other words, this is like the surface of a balloon that comes around the Earth. It's like a balloon. And as that spins through space, it scrubs the particles that are in space, the light coming at it, and it separates. It literally separates the white particles from the black particles. It's 1,500 degrees Celsius out here. It's ionosphere. What does ions mean? Only electrons, only the white part, only the white burny part. And I'm going to show you this. Now, if this is 1,500 degrees here, why is it minus 80? When I say 1,500, that's Celsius. Minus 80 is Celsius as well. This is hundreds of degrees below zero, and this is thousands above zero. why is there such a separation zone? Because of the black and the white. Everything is a dipole. That's the nature. And so the dark particles are coming to Earth, and that, again, is what creates gravity. There's more dark particles on Earth than the white particles. Gravity means it's going to pull the white particles down towards it. And everything down in here has white particles and dark particles. Up here, we're removing a lot of the white particles. So a lot more dark particles come down to make the Earth gravitational, which will suck the white particles to it. That's how electricity, lightning, static, everything, right to ground. And that's the difference right here. This is the zone that separates the white particles from the black ones. Okay, this is going to show you exactly what happens in the ionosphere. The ionosphere has separated the white from the black, and that is exactly what happens in an atomic bomb. The first thing is all the white radiation goes out, and it has no mass, it just has energy. So when this came through the ionosphere, it didn't explode it, it didn't break it, it just infused it with electrons. And you're going to see that happen here. This is in very slow motion. They have an atomic bomb back here. They have cameras facing this way and in a hardened enclosure. They can't get damaged, they're not going to get burnt up by they're facing away from the explosion. Now, watch what happens. First of all, there'll just be an enormous white glow. And all of the poles, the wires, everything burns up. Nothing moves, not even the smoke. Watch this now. Because this is the separation of the white particles coming first and then the black following. Here it goes. This is what an atomic bomb does. The first thing you're going to see is just everything glows. And I'll stop it when that happens. Boom. See that? This is a complete irradiation. This is what the ionosphere is. This is identical to the ionosphere. Identical to the ionosphere. It's saturated with these white particles, these glowy little particles that don't push, they don't show, they just burn. And I show you them burning. So here goes this house. Don't forget, this is the ionosphere. And this house is coming through the ionosphere. Right? And this is the house coming through the ionosphere. And it's just smoking up, smoking up. This isn't smoking up because it's not absorbing, it's not like moist. Moisture and combustible things smoke up fast and they burn fast. All right, here goes. There's just nothing. It's not even blowing the smoke. Nothing. Nothing. Look, all up here, you see this? Every single thing that can absorb electrons is absorbing it. And it's just like that meteorite or those asteroids or whatever coming through our ionosphere. And they just burn everything up. Now, if they came straight down like this, I don't know, maybe that would not burn it up so quick. If they come in this way, they're going to come in all different ways, depending upon how the Earth is spinning, how we're going around the sun, and how that thing hits this side or that side or up the top or on the bottom. It's going to be all different ways. So that's why there's so many different types of meteorites, and some of them get really cooked up, some of them not so much. Now the black stuff is coming. This is what an atomic bomb does. It separates. It's fission first to separate the white from the black, and then it's fusion. And here will come the black now. Boom. I just stopped it. This is the black, just like a big black wave coming across here, moving everything out of its way. This is like a bulldozer. Watch it bulldoze. See? Boom. It just keeps going and going and going. Now, that is an atomic bomb, and that is the separation of the white, which is our ionosphere. It's exactly what the ionosphere is. And if you could measure the temperature here, I'll bet you this would be below zero. I'll bet you this would be much below zero right here. Because there's just no energy here. There's just nothing but mass. And it's identical to what we discovered in the light research. Identical. Okay, I've tried and posted and sent an email and all kinds of stuff, and I get no responses. But this sample that came back from Bennu was dropped off in September 24th. The outer capsule opened very easily, and they had in their hands 2.48 ounces of dust. And that's, I don't care. That's the dust you can test right now, and it will be blood. There's no reason they can't take a zillionth of an ounce and test it. It's going to be blood. The head contaminating majority of sample remained tightly sealed against the team's best efforts. So in other words, they couldn't even get the thing open for over 3 months. And now they finally got it open, the one that they don't want to contaminate. That's fine. That's perfect. Have a nice time with that. The stuff that's already contaminated, test a little bit of it. If they're not afraid to, just test it and see if it comes out to be the same thing as blood. It will be the same as blood. I can absolutely 100% guarantee you of that. And if you don't see a heart there, and you don't understand what a heart looks like, and you can delude yourself into thinking this is just a rock in space, and it has nothing to do with a heart, then that's your issue. And if you can think that that's just another chunk of who knows what, and it has nothing to do with a hip joint, and this blowing smoke out of here, which is nothing but hydrocarbons and gas grill smoke, and astronauts thinking that space smells like steak, that's your issue. This is not my issue. But we're all paying for this. This is over $1 billion. And that's just the start of it. That's just probably the hardware. When you get into all of the other people that are working on this and all around the world, how they're going to take the years and years and years. We'll study this stuff they're going to seal it away and they'll never contaminate it and they're going to be real careful. Well, that's fine. But it doesn't require billions of dollars to do this. I think we could use the money in better ways, to be perfectly honest with you. So milking an asteroid, I don't think is the best solution to our situation we're in right now. All right, I showed you that list of all the different metals. These are all these different metals, and they have crystallized and flocculated in their liquid state together to create these crystals. They will crystallize together. Well, that, my friends, right there is blood, red, and that is the black, which is vein and artery. That right there is the artery. You see that red blood? What's that doing there in the center or inside of a meteorite? And what's the black one doing? Well, I know exactly what they are because I believe this is a liver. And anything that's saturated with blood is going to give you an iron meteorite. And livers are basically saturated with blood. Then they don't have all the vascularization as a lung, and they don't have the valves and all that like the heart. So we saw the hearts. Now let me show you a gigantic lung. These things were just gigantic. It was all written in history, and this is what upsets people like Avi Loeb from Harvard, who is claiming, well, it could be a spacecraft. Well, he's outside the box, but he's still got 1 foot in the box. He just can't get to where I am. You see that? That is a lung, my friends. And that came through space and smelted just in a perfect way where it was in the ionosphere without getting disrupted too much and smelted, got hot as it could possibly be, gave everything that was vaporizable. As you saw, just like that house, just everything vapored up. And then what you were left with was iron. This is not a meteorite, this is a terrestrial lung, and it's just evacuated everything basically. So you can see the same structure. You see right down there, watch this. You see that little dot right there? That's a blood vessel. That's got blood still red, and I'm sure you can possibly get something out of there, some kind of enzyme. Although I don't know, at a certain temperature, you'd certainly expect them not to work anymore. But this one here is an iron meteorite, and it has a catalase in there. It foamed all up when I put it in there. Almost all the fibrous stuff in here burned up. I can see very few fibers left, but all of the blood still inside, deep inside, didn't seem to burn up and blow out. This, it looks like almost everything evacuated, and that's all they got left is metal. But inside this, if I cut it wide open, I bet you I could find almost some raw red blood in there. Because this one didn't heat up like that one did. The bigger they are, the hotter they get. But if they come through just in the right way, like this must have come through just exactly the right way so it didn't explode. But it maintained itself as a lung. Okay, once again, get an anatomist, get some biologists, get some autopsy people. This is a lung. That is the same lung as this. It is flat as a pancake on the back because there was a great flood and everything died in that flood, basically almost everything on Earth, and they were protected by this fascia. I called it fascia-facilitated fossilization. The coating protects things. Now, this coating here, look very carefully. You see all these little white fibers all over the place? Here's where I took the blood out of here. I drilled a little tiny pin drill down inside here, took the blood out and sent it off and it tested human. And this one here actually leaked blood out of it. You see these little tiny holes, little red spots? Some of them leaked, actually little bubbles of blood came out of it. And these are the alveoli, if you can see them here. This one turned completely to quartz. And they preserve in different ways, just for crazy different reasons. And these are the circles here that are the alveoli, and it just was super saturated with silicon, and that just filled in all the voids, which there was just nothing but voids, basically. And this one here, for some reason, the coating protected it, and everything inside, if I cut that wide open, you'd see all the stuff, the plumbing of the lung. Now this one has, like I say, some of the blood came right out of it. So what I'm going to show you in the microscope is one that came through space. And what you're going to see is this here, and where all the red stuff was, it basically turned black and burnt off 99% of the fibers. And you'll see a few fibers, and you'll see almost all black behind that. And then you'll see a whole batch of alveoli here and there, which have become exposed but burnt off. But you'll see the red blood inside of them. So let's get back to the microscope, or get to the microscope. Here we go. Okay, let's get started with the meteorite is here. We're going to be looking in the microscope, and we're a little ways off now, but I'll be able to show you the fibers and all that stuff, and the blackness, where this one here has redness. This one will have blackness, and it will have almost all the white fibers burnt off. All right, here's that lung. This is that little iron lung. I say came through space. I'm absolutely certain of it. Here's some of the little white fibers that are left. Very few. The other one's just saturated with it. And the surface is burnt through, and some of the alveoli holes are sticking up through there. Quite a few of them, actually. You see it's all over here. All right, now I'm going to put a little hydrogen peroxide in this area here, and then focus down into it and see if we get a catalase reaction. We should. I did this before a while back. I don't know, not too long ago actually. I'm hoping I'll be able to get something good out of here, especially if you go deep inside of it. It should be blood in there, and it should bubble up really good. Let's find out. All right, I'm going to put the hydrogen peroxide on here now. And you normally can see a real nice change in the texture of the surfaces. You know, you can see the colors and everything. So now let's see if we get any bubbling. We should get some bubbling out of that. And don't forget, this came through space, so, you know, there may not be any. I'm seeing a little flickering going on. Hold on. If it was really saturated with blood, it would bubble like crazy. It would just fizzle all over the place. Oh, I'm seeing some. You see, when you see that white fuzzy stuff? That white fuzzy stuff is the catalase reaction. Not much there. But I might be able to get more out of there if I put more in. You see, all the catalase out here has been degenerated, it's been destroyed. But way down inside that little hole, I'm going to try to force some more in there. All right, let's see what happens now. There it goes. Now it just starting to pump. There we go. There we go. Now, I'm going to get right down on top of it because we're way off it. All right, I'm going to come right down on it. You should see a lot better reaction down there. Hold on. This takes a minute. This takes a minute. There it is. You can see it boiling down inside that hole. You see it down in there? Let me tweak in here. The surface has been burnt up, but down inside it's a different story. I know you can see that, and it's bubbling up over here too, but down inside where there's a lot of blood still in there, or whatever. All I can tell you, there's a lot of catalase still in there, and I mean quite a bit. Look at it now, bubble. I just pump some more in there. Look at that baby go now, bubbling like crazy. Look at those bubbles come out. This thing is saturated with catalase. Catalase is an enzyme. And it's only created by biological things. Look at that bubbling down in there. It's sort of bubbled off a lot of the big bubbles. Now we're just seeing the little bubbles bubble. Let me see if I can get closer. Well, there's zero question that that's a reaction. That is a very strong reaction deep inside, not on the surface. The surface has been cooked. An enzyme is an extremely exotic chemical, and if you overheat it, it stops working. Some of the enzymes that are in your body at a certain temperature, which is like 104 or 105 degrees, they stop working. That's why you die. Enzymes, you have to have them working 24/7 flawlessly. Look at that. It's just bubbling like crazy down there. All right, I'm going to freehand this, so it's going to be a little shaky. This is the bony meteorite. All right, this is the bony side. But you see all of this bloody looking stuff in there. And then this is where it cooked off on this side, which is where this is just turned to iron, which is the blood that's boiled out from this bone. You can see the bone. All right, that's about the best I'm going to be able to give you. That's the bone right there. And this is the blood that boiled out and had to get to 2,500 degrees or more before it would turn into this iron. It becomes magnetic. You know, it attracts magnets. It's iron attracts magnets. It's not magnetic. But you see this? This is where the blood boiled out and just exploded out the end and turned the blood into metal. But we still have some bone attached to it. All right, so that's my case there. Okay, so now my exceptional friends, I believe I have demonstrated that as far as I'm concerned, all of these things that are in space are biology. The things that have hit the Earth, the meteorites, comets we see, asteroids, as far as I'm concerned, I see nothing that is not biology. I can find nothing. And I know for a fact, if they will test that stuff from Bennu, just the scraps, they will show to be precisely what I showed as whole blood, plasma, and serum. It'll be that sort of stuff. And it's right off of here, and as I've shown you, the black and red is from blood. There's no question about what we're talking about here. So it's going to be $1 billion. I don't know what exactly they're trying to accomplish there, but I can tell you what, if they're looking for what this came from and the origins of life and so forth, they got to talk to Roger, because not a single one of them is willing to speak about it, first of all. Secondly, I don't know if they're able to understand it. I just can't imagine they're not able to understand it. That I can't imagine. It's just impossible for me to believe that I can show this for years, 10 years or more, and have nobody be able to understand it. That just doesn't make sense. You guys can understand it. I know you can. This is how you milk an asteroid. All right, I love you all, but I don't like paying for this kind of stuff and have them not engaged in the science and always touting themselves. We're just trying to do everything we can to figure this out. I don't see it that way at all, my friends. All right, I love you all. Let's try to talk to somebody. If you got anybody you can talk to, I am cut completely out of the loop because of my claims and statements. They treat me like I'm an insane person, that I'm kind of dangerous. Well, that's not the case. I'm trying to solve problems instead of walk around in circles. This is costing a lot of money per circle, and there's a lot of circles going on. Virtually everywhere I see in academia and science, it's nothing but circles. All right, so I love you all, and stay tuned. That's all I can say. Spread the word, share, subscribe, make sure you ring the bell, and then keep coming back, because they've been not giving people notifications. That's what I'm hearing. All right, love you all. Bye.